Imagine writing a piece of code so cleanly, so perfectly organized for human readability that it just accidentally tanks your entire system's
Yeah,
performance.
yeah, the classic trap.
Right. I mean, if you've ever spent hours staring at a CPU profiler, just wondering why an elegantly written function is suddenly a massive bottleneck, then you know exactly the kind of paradox we are diving into today.
It is incredibly frustrating.
It really is. And welcome to today's deep dive, by the way. Our mission today is to unpack this very specific paradox for you. We're not talking about broken logic or like syntax errors here.
No, not at all.
It is about the hidden architectural traps we set for ourselves when we try to make things look, well, a little too tidy.
That paradox is arguably one of the most difficult thresholds a developer actually has to cross.
Yeah.
You organize your logic based on how your brain processes the domain, and in doing so, you just completely ignore how the compiler actually evaluates the execution context.
Which is exactly the tension at the heart of our source material today.
Right. We are looking at a deeply technical, very specific developer's log from a blog called Notes on Haskell Programming.
And specifically, this is part 153 of the series.
Part 153. That is dedication.
I know. The fact that the author, someone named Ang, is writing part 153 on June 4th, 2026, I mean, that tells you everything you need to know about their dedication to the craft.
Seriously.
The entry is titled Refactoring for Purity in Keywords Extraction. And, okay, while that sounds like a hyper-specific Haskell manual, the actual content is a masterclass in software architecture.
It really is.
Ang documents this seemingly microscopic tweak, literally just shifting a single line of calculation out of a local block that suddenly unblocks a massive bottleneck, and it completely redefines the purity of the system.
It's a brilliant artifact because it captures a raw aha moment,
Right.
Ang isn't writing a textbook on theory here.
Right.
They're looking at their own code base, realizing that a previous attempt to optimize the system was actually entirely unfinished.
They thought they nailed it.
Exactly. They thought they had solved the problem. But looking closer, they noticed they had just, pushed the friction into a totally different layer of the application.
Okay, let's unpack this. Let's look at the before state of Ang's code, because it is the perfect trap.
Oh, it really is.
It's a trap any experienced developer could easily fall into. So Ang was calculating an array of keywords, and to keep things organized, they placed this keyword calculation inside the local scope of a function called applyIndex.
Specifically, it was nested inside a where block.
Right. Now, for anyone writing Haskell, putting a helper variable in a where block under the function that uses it, I mean, that feels like the most natural, idiomatic thing in the world.
What's fascinating here is how the psychological desire for cohesion actively ruined the machine's efficiency.
Yeah.
Ang explicitly points out that their previous version of the code had prioritized cohesiveness.
Which sounds like a good thing.
It does. By putting the keyword extraction logic right next to the index generation logic inside that where block, the developer's brain says, great, the things that relate to each other are physically grouped together on the screen.
Everything's nice and tidy in its little box.
Exactly. But local scope in functional programming isn't just a folder for organizing text. It dictates the evaluation lifecycle.
And that lifecycle was brutal in this case.
So brutal.
Because of that placement, every single time the applyIndex function was invoked, the program entered that local scope and was forced to completely reevaluate and re-extract the keywords from the base tokens.
Just think about the computational overhead there.
It's crazy. It makes me think of a chef making soup.
Oh, I like this. Go on.
So imagine a chef who is tasked with making 50 bowls of soup.
Okay.
But instead of just reading the recipe once and keeping it in their head, this chef insists on complete rereading the entire recipe book from page 1 before serving each individual bowl.
That is exactly what's happening. It is CPU cache thrashing, essentially.
Yeah.
It is as if you have a critical piece of reference data, but instead of loading it into a global register or a higher level cache where it can be read instantly, you purposefully dump it out of memory the second you are done.
Just throwing away the recipe book.
Right, forcing the system to fetch it all the way from the hard drive for the very next instruction, over and over again.
It's maddening.
Ang specifically uses the phrase reevaluation of the keyword's extraction. In a functional language that relies heavily on complex data parsing, redundant reevaluation is a silent killer.
And it's the kind of inefficiency that doesn't break your unit tests, right?
Not at all.
The output is perfectly correct. The compiler doesn't throw a warning, it just makes the machine sweat for absolutely no reason.
Yeah, exactly.
Apply index is supposed to just map entries, but because of that local where block, it stops the presses to reconstruct its entire understanding of the keyword dictionary from scratch on every single pass.
Which forces us to look at the architectural environment around ApplyIndex. If ApplyIndex is thrashing the system, the solution isn't to optimize the extraction algorithm itself. The solution is to question why ApplyIndex is responsible for extraction in the first place.
Yes, asking the bigger question.
Exactly. This requires a shift in how we view the boundaries of our functions.
Since the chef is wasting time rereading the recipe, how did Aang actually fix the code?
Well, by physically shifting where the work happens.
Right, which brings us to the mechanical fix, and frankly, looking at the code diff, Aang provided the before and after text. The fix looks suspiciously simple.
It really does.
Aang physically lifts the heavy keywords calculation completely out of the apply index function and moves it up into the broader scope of the calling function, which is named tokens to pandoc.
Let's trace that new data flow. The broader function, tokens to pandoc, is now the orchestrator.
Okay.
Aang outlines its specific parameters. It takes a format, abbreviated as FMT, it takes the raw tokens, and it takes a year.
Got it.
Its primary job is to fold the blocks together. But in this new architecture, it also takes on the initial heavy lifting. Using a case statement, tokens to pandoc calculates the keywords just once up front.
It computes it once, caches it in memory, and then passes it down.
Precisely.
Apply index is entirely stripped of its local where block calculation. Instead, apply index is now simply handed the content and the pre-calculated keywords, which Aang abbreviates in the new code as cake.
All right, the cakes variable.
Yeah, so the new invocation is incredibly lean. It's literally just apply index content cakes.
The physical movement of the code is minimal, but the conceptual shift is massive. By moving that logic up, Aang achieves what they explicitly call decoupling.
Okay, here's where it gets really interesting, though, because I am looking at this architectural shift, and I have to push back a little on the idea that this is a pure win.
Okay, let's hear it.
If we lift the extraction logic out of apply index and dump it into tokens to pandoc, aren't we just violating the rules of good design in a different way?
How do you mean?
Well, now tokens to pandoc is responsible for folding the blocks, managing the format, managing the year. AD, it has a case statement to extract keywords. Didn't Aang just pass the buck?
That's a fair question.
Right. Why is overloading the parent function actually better than letting the child function handle its own business?
It is a critical distinction to make. On the surface, I agree, it looks like shifting the bottleneck from one side of the desk to the other.
Exactly.
But we have to differentiate between a function that orchestrates logic and a function that applies logic.
Orchestrates versus applies. Okay.
Yeah. Tokens to pandoc is an orchestrator. It already owns the tokens parameter. It is the boundary where the raw data enters this part of the system.
Oh, I see.
Therefore, it is the mathematically correct place to transform those tokens into a static map of keywords.
So it's about defining proper domain boundaries.
Precisely. Aang notes that this move separates the generation of the keywords from the generation of the index. They're decoupling two fundamentally different operations.
Right, they aren't tangled together anymore.
In the old code, generating the index and generating the keywords were hopelessly tangled. You couldn't invoke the indexer without accidentally invoking the keyword parser.
That makes a lot of sense.
By severing that knot, tokens to pandoc does the setup and apply index does the execution.
That distinction between setup and execution really clears it up. Tokens to pandoc might be doing a bit more orchestration, but it is only doing it once.
Exactly.
Just once. Buck isn't just passed. The actual weight of the buck is reduced because we are no longer paying that massive reevaluation tax in the child function.
And that mechanical decoupling is the exact bridge to the overarching philosophy Aang is exploring in Part 153.
Right, getting into the deeper meaning.
Because the title of the post isn't making apply index faster. The title is Refactoring for Purity in Keywords Extraction. The primary goal wasn't just speed, it was architectural purity.
Purity. So what does this all mean for the developer at the end of the day? Let's dig into Aang's definition of a pure function because it gets to the very heart of functional programming.
It really does.
Aang states that the core functionality of apply index is now purely searching and replacing keywords as index entries. But the crucial part of Aang's description is that apply index does this without knowing how to extract those keywords from the tokens.
And that concept of knowing nothing is perhaps the most powerful design pattern in software engineering.
It's kind of counterintuitive, right?
It is.
Yeah.
We often talk about the single responsibility principle, or SRP, as a function doing one thing well.
Right.
But the inverse is equally important. A function should be entirely ignorant of anything outside its strict jurisdiction.
Ignorance as a feature.
Absolutely. Think about your assembly line analogy.
Right. Yeah, it's like an assembly line worker whose only job is to hammer a specific nail.
Exactly.
If they also had to forge the hammer and smelt the iron, the whole factory would grind to a halt.
That is the perfect way to look at it. Before this refactor, ApplyIndex was smelting its own iron. It was too smart for its own good.
It knew too much.
It knew the intricate details of token structures. It knew how to parse them. It knew how to filter them into keywords. And then it knew how to generate an index.
Wow, when you list it out like that, it's doing so much.
It was entangled in the how of its dependencies. In a pure functional paradigm, a function shouldn't know how its ingredients are made. It should just receive them as parameters and return a predictable output.
Because the moment a function knows how to make its own ingredients, it becomes fragile.
Exactly.
If the shape of the raw tokens changes, the old apply index would break. Even though the logic for actually generating an index hadn't changed at all, that completely violates the core tenet of SRP.
Which is why the new invocation ApplyIndex contents is so robust. It explicitly declares its dependencies.
Right.
Give me content, give me an array of strings, and I will give you an index. It doesn't care if those strings were parsed from markdown tokens, fetched from an external database, or just hard-coded by a developer.
It's completely agnostic.
Yes. Its purity guarantees referential transparency.
If we connect this to the bigger picture, that guarantee of referential transparency brings us directly to the massive operational rewards Aang highlights at the very end of the developer log.
The ultimate payoff.
Right. Testability and composition. Let's start with testability, because anyone who has maintained a large code base knows that testing tangled functions is just a diagnostic nightmare.
Oh, the testing overhead for the old architecture would have been brutal.
I can't even imagine.
To write a unit test for the old apply index, you couldn't just test the indexing logic. You'd be forced to mock an entire array of raw tokens, pass them into the function, and basically hope that the hidden where block evaluated them correctly before the indexing even began.
So you aren't even writing a unit test at that point.
No, you are essentially writing an integration test disguised as a unit test.
Right, because if the test fails, you don't actually know where the failure occurred. Did the indexing logic fail to replace the string? Or did the where block fail to extract the keyword from the token in the first place? You have two completely overlapping variables in a single test case.
But look at the decoupled version. Aang explicitly states that this separation makes it easier to test in isolation.
Because apply index now only accepts a plain kex parameter.
Right. You don't need a token parser to test it. You just inject a fake array of strings, like literally just keyword 1, keyword 2.
Wow.
If it places those strings into the index correctly, the function is perfect. You have achieved total isolation of the variable.
It strips away all the mocking infrastructure. You aren't setting up a massive state machine just to test a string replacement algorithm.
Exactly.
And that exact same isolation is what enables the second reward Aang mentions, composition.
Composition is the ultimate goal of the functional paradigm. We want to build systems out of small, reliable, interchangeable blocks.
Lego bricks.
Yes, Lego bricks. When a function relies on a hidden local evaluation of a complex domain object like those tokens,
It is permanently tethered to that domain.
it carries baggage.
So much baggage.
You can't just pick up the old apply index and use it in a different part of the application because it drags all that token parsing machinery along with it.
That is exactly the problem. But the new apply index content is completely generic. It is a pure search and replace mechanism.
So you could reuse it anywhere.
Theoretically, yes, you could lift that function out of the tokens to pandoc pipeline entirely and plug it into a completely different feature that needs to index plain text documents against a list of search terms.
The function wouldn't care.
It doesn't care at all. It is a perfectly composed Lego brick.
It is genuinely amazing to trace this back to the origin point. We are talking about sweeping changes to test infrastructure, the creation of highly composable utility functions, and the enforcement of strict architectural boundaries.
And all of it stems from Aang looking at a where block in part 153 and realizing, wait, this is reevaluating too often. It really proves that in software, the macro architecture is entirely downstream of the micro decisions.
So true. A system doesn't become rigid and unmaintainable overnight.
Right. It's a slow process.
It becomes rigid because of 1,000 tiny concessions to cohesiveness. putting things close together for the developer's convenience while just completely ignoring the evaluation cost and the coupling it creates.
And untangling those concessions is what separates functional code from truly pure code. The mechanical act of moving a calculation out of a local scope and up to an orchestrating function like tokens to pandoc, it isn't just a physical cleanup.
No, it's much bigger than that.
It is a philosophical shift toward the single responsibility principle.
By explicitly separating the generation of data from the application of that data, you remove the hidden state.
You eliminate the CPU thrashing.
Exactly. And you leave yourself with a code base where every function does exactly one thing, flawlessly, with absolute ignorance of the world around it.
It's beautiful, really. And, if you've ever dealt with a tangled system, whether that is a legacy code base, a massive spreadsheet, or even just a really complex operational process at your company, this developer log offers a profound mental model.
It applies everywhere.
It does. The instinct is always to group related tasks together to make them feel cohesive. But as Ang discovered, true efficiency often requires decoupling those tasks.
Yeah.
It requires pulling the heavy lifting up to a central orchestrator so that the individual workers down the line can execute their single responsibility without constantly stopping to reevaluate their resources.
It is a lesson in defining clear boundaries and trusting that pure, isolated components will ultimately form a stronger, faster whole.
And that leaves us with a really compelling thought to mull over today. Eng referred to this decoupling as a minor optimization that massively improved composition and testability.
A minor optimization with major consequences.
Right. So think about the intricate, highly cohesive processes in your own workflow. What hidden reevaluations are silently draining your resources simply because you haven't separated the setup from the execution?
That's a great question.
And what level of speed and clarity could you unlock if you finally decoupled them, allowing every part of your system to function with absolute single-purpose purity?